And without further ado, I'm very pleased to introduce Vera Serganova from the University of California, Berkeley. And we're going to continue our review of the undergraduate math curriculum, which was started on Monday. Paul Balmer told us about the analogues theorem, and Vaintrob explained the Chinese remainder theorem, and Vera is now going to help us understand properly the Sylow theorems in the context of support varieties for lead supergroups.
Thank you very much for the introduction. Can you hear me well? Okay. So first of all, I'm very pleased and very glad that I'm here to celebrate Anne's birthday. And his research has a great impact on my research. Talking about missing opportunities, I think Dan just left Yale with his PhD, and when I arrived, and maybe if we met before, all this I'm going to talk about will appear early. Okay, so let me start with giving you, most of you already know this, but let me just mention that I'm going to consider new Frobenius tensor categories over a field of characteristic zero. And in some way, they are very analogous to modular representation theory of finite groups. And what we will see today is a lot of analogy. So I put here ground field as C because at some moment I really need C, but in principle, all this is generalizable in algebraically closed field of characteristic zero. So what I'm going to consider is I'll start with the symmetric monoidal category of supervector spaces, which are Z2 graded vector spaces, and all the operations of duality and tensoring as before. But what is different is the braiding. So we have this, I made it red, the sign rule, and that works for all homogeneous elements. Otherwise, you extend it by linearity. Okay, so as soon as you have such a category, you can do whatever you want with it. For example, you can even do algebraic geometry in this category, and people do. And you can consider an affine group scheme in this category. In more simple words, this is a commutative Hopf superalgebra. And what we always have, if we have such a Hopf superalgebra, we can quotient by the ideal generated by odd elements. And when we quotient, we get a usual Hopf algebra. And that means that we have usual algebraic group. And this usual algebraic group is called sometimes underlying group. And then it is not very difficult to check that the category of representations of this group is Frobenius, if and only if the underlying group is linearly reductive. Here I mean that I allow non-connected group, but groups of semi-simple categories. So in particular, if we don't go to superspaces, we don't have anything interesting. We just get semi-simple categories. Of course, they are very interesting from some different point of view. And as soon as we have all this, it is only natural to ask about the Balmer spectrum of the corresponding stable category. And that's what I'm going to discuss. I would like to spend a little bit more time on this. We can also, of course, pass to the Lie algebras in characteristic zero. This is especially easy to do because more or less it's the same. And that's really what you can consider this category, the category of representations over the corresponding Lie superalgebra, which are direct limits of finite dimensional representation, semi-simple over G0 part. For example, if your G0 part is simple, there is no restriction. So we can work slightly bigger category. Somehow for support variety, it's not so important which category to study. I don't want to give a traditional definition of superalgebra, especially that most people would. to do it, but I would like to say that there is another way to look at it. And if you look at the superalgebra, you have the zeroly algebra, which is denoted by G0, and the module of G1, G0 module, and you have one additional data, which is bracket on odd element, which is actually symmetric because of the sign rule, and satisfies this additional condition that for every odd x, we have such a relation. And of course, if we start with quasi-reductive supergroup, which means its underlying group is reductive, when we get the superalgebra, which is also quasi-reductive, and here is the natural definition of this. And then you know what you can do. You can consider the Harshchandra pair. You can consider the superalgebra, and inside, and then you have the usual group, which is whose the algebra is G0, and you can work with this Harshchandra part, where it basically is an equivalence. This is not surprising because in reality, what is happening, your scheme is the scheme of nilpotence. These nilpotence are generated by odd elements. So the nilpotence don't give you real geometry and topology. They give you only algebraic part. So this remark, the last remark, is due to Kasul, and it's at constant. It's about it was noticed in the 60s actually, but proved very carefully and most generality by Maslow. So here I give you an example. So the first example is just a Abelian superalgebra, which means that we don't have even part at all. So what is happening if you look at universal enveloping, this is just Grassmann algebra on G1, which is clearly Frobenius category, and people, of course, studied it before. When we can slightly upgrade this example in the case 2, when you take a semi-direct product, so we actually have now a reductive group G0, which acts on G1. So, and then we have classical cases, which both John and Slava were talking about, John Brandon. So we can consider supervector space. It has 2 dimensions, 2 numbers, even and odd dimension, and you have an algebra of automorphism. Sorry, I'm talking about groups now. Group on automorphism. When we have a beautiful thing, so you see in super case, you have analog of determinant, and this is called Berezinian. And so you can go to SL, and this is another supergroup. Well, we can have quadratic form, and this quadratic form as bilinear symmetric form, if it is even, we get what is called orthosymplectic group. It is just again orthogonal symplectic group, but we have 2 more new, maybe the most interesting. One of them is called periplectic, and that means that if your odd and even dimension of the space are the same, you have an odd symmetric bilinear form. And you can look at the group which preserves this odd symmetric bilinear form. And it is called periplectic, and I think by some reason, this name periplectic was given by D. And when we talk about, John was talking about this, isomeric or queer. So it was before queer, but now Andrew Snowden invented this term isomeric for the supergroup QN. And this is a new structure on your superspace, which is preserved by QM. Basically, this is an odd isomorphism. So in particular, the language of enriched categories, this is which John Brandon was talking about last time, is especially useful for this category. So what I would like to say, but there is some observation that if you, so whenever I have a G1 odd part and I look at the action of the corresponding algebraic group G0, so I use Latin script letters for the group, for the supergroups. So when I take the invariance, in many cases, it's just a polynomial ring. In many interesting cases, it's just a polynomial ring. And it's kind of interesting to understand that. So then Katz made this classification of this. He noticed that, but there is no conceptual explanation why these are very nice representations, indeed, which we encounter in this book. Okay, so now I would like to give you a slight history of the situation with these support varieties. So it's more than 20 years ago, Michel Defleur and myself started to look at the following construction. We take inside the odd part of our superalgebra elements such that their commutator with the same as 0. It is a self-commuting koan, and it is kind of useful in computing, for example, cohomology of these superalgebras. And so we define associated variety in the following way. So we have this functor, which I have to call ds. It's not very modest, but people call it ds now anyway. So whenever I have a module and I have an element such that the commutator of itself at 0, it means that x squared is 0. And if I have something which x squared is 0, I have cohomology. And so I define this functor, and then I can characterize a variety xm consisting, this is a variety in G1, and it consists of points in self-commuting points, just as this cohomology are not 0. Okay? So when we did this and we started thinking about it, we didn't know anything about support variety for finite groups. We didn't know much about support variety in general. And our motivation was completely from a different source. It was unitary representations, Harris-Chandra module, associated variety there. And that's especially was motivation for Michel. And then very soon after that, then with collaborators, Brian Boy and John Kujawa, started the theory of homological support variety. So the first thing which we would like to ask in this case, what is the extension of the trivial module? That is the algebra of extensions of the trivial module. And it has a nice description in this case, because you just have a relative homology. And this is the ring of invariance with respect to G0. So they developed the theory of detecting subalgebras, which I'm going to talk later a lot. And there are several very interesting papers, but one of them for me is very important. When they really constructed Balmer spectrum for the V superalgebra GLMN1 in my list of classical list superalgebras. So now I'm going to pass to, so I'm going first to upgrade this DS factor. Instead of considering elements such that their square is 0, I just take a commutator of x with itself, and I assume that it is a semi-simple element in the Lie algebra G0. This is a reductive Lie algebra, so a semi-simple element means that it acts diagonally on any representation of the algebraic group, corresponding algebraic group. And I'm going to take slight upgrade. I take the kernel of x, and I take the quotient by the intersection of the image and the kernel. Another way I can say, but I take the commutator of x with x, take invariance of m with respect to this even element, and then I take homology inside this. So what is nice about it, so it is clear why it is upgrade, because before we consider only the situation when this commutator with itself as 0. So now we are going to consider, so this factor is symmetric monoidal factor, and this is very important. And we define Vm as the set of all homological elements such that this factor is not 0 on it. So you can think about it in a different way. So what is this? This is homological element. It has this elements, G1 homological element. It becomes clear why. So you take this X, and you consider minimal subgroup in the corresponding algebraic supergroup with this Lie algebra. So basically, you consider the supergroup generated by this element X. And the condition that X is homologically is exactly the condition that the corresponding group is reductive. So what we are really thinking, think about like embedding a cyclic P group or any cyclic group inside the finite group. So you can think about the supergroup generated by this odd element, and we look at all the smallest smallest elements, and we restrict to this subgroup, and we are asking when our representation, when restricted, is not projected. So this is a good candidate for a support variety. It satisfies these nice properties here. So it is obviously by satisfy the tensor product property. And okay, it is clearly conical G0 invariant set. And if a representation we start with M, if the module is finite dimensional, then this is a closed conical set. So one of the theorem which we do with Julia, Alex Sherman, and myself, and this is very recent theorem, but we have a projectivity detection in the most generality. So whenever I have an object in this category, the name is projective in and only if nu m, Vm is 0. So this requires extension of scalars. If my representation has a pretty big dimension, I might talk about it if I have time later. Well, and so conjecture what we have is that if I take corresponding stack and take approach of the stack with topology induced in the topology on G. One, that is exactly the Balmer spectrum of this category for any quasi-reductive. So first of all, the result which I mentioned before by Brian, John, and Dan implies this result. And second, this result, this conjecture is certainly true if you consider this order-billion case, because this is just Kazoo duality. Remember, order-billion case is just representations of exterior algebra. So, and this is the Kazoo duality, and BGG correspond with it between derived categories of quasi-coherent shapes on projective space and representations of exterior algebra. So what we just noticed very recently, but actually can prove it for all classical and simple, but this is still a progress. But somehow we realized that we probably can prove it for all classical and simple. It's very interesting, but I'm not ready to talk about it right now. That's why it isn't green.
So G1 of, is that a closed subset of G1?
Sorry. That's a good question. Only just let me go back. Yes, actually, no.
Oh, not in general.
Not home, not at all. Yeah. I mean, of course, in a billion case it is. In general, it is not. It is not. It is very important. I should have said about it. So, but you know, you work with this step as a topological.
Right. So it's a locally closed set.
Hmm?
It's a locally closed set in the variety.
Right, right. You just take the intersection topology. Exactly, that's what I. Oh my! So now I'm jumping to something which I didn't have slide of. So now I'm going to actually, basically, I'm going to lead you to the proof of this theorem, and maybe I should speed up. So, what is the main point of this talk? If you miss everything else, that the methods for finite groups and positive characteristics work very beautifully and amazingly beautifully in the case of supergroups. And the first thing you can think about is what are Sylow theorems, right? Because the Sylow theorem clearly plays a very important role in representation of finite groups. So I'm going now to quickly do the thing about finite groups very, very quickly. So you have a finite group prime characteristic, algebraically closed field, prime characteristic. The P group is just a group of order Pn. So we know that P group has one simple module, and this is trivial module. And okay, I wrote it here, but that's there is also maximum subgroup. They are all conjugate, and the number of Sylow subgroups is one module P. Oh, oops. Oh, I don't know what happened. I need some help. Sorry. I don't know what happens in, honestly, I probably, excuse me, please. Where I am? Okay, okay, sorry. I don't know, yeah. Okay, anyway, let's go. So now I'm going to introduce something which is not conventional, but I would like to discuss it because I would like to discuss it in the situation of supergroups later on. So you see, I use these usual Latin letters for finite groups and script Latin letters for supergroups. So there is a very natural class of subgroups which might be called splitting, and they satisfy these conditions 1, 2, 3, 4, which are clearly equivalent. And this is very simple statement for finite group, but every splitting subgroup is a subgroup which contains a Sylow subgroup, right? So for example, if you look at the property 4, but if whenever you have an exact sequence and it splits over K, then it splits over G, what you do, you take average over cosets and you can go back. So in particular, if I have a splitting group, I can go to the stable categories and I can check projectivity. I detect projectivity on the splitting subgroups. And of course, this lemma, I already explained it, but suppose I want to look at minimal splitting group. This is exactly the Sylow subgroup in positive characteristic, right? That's exactly the Sylow. So this is a little diagram. So I have inside G, we have P groups. We have Sylow subgroups. So splitting group is the one which contains a Sylow subgroup. So why this is important? Well, probably most important thing is that you can consider also so-called, why all this is important, because you can consider what is called elementary abelian groups, which are direct products of cyclic group of order P, and we can detect projectivity by this very famous theorem. We detect projectivity by restriction for elementary abelian subgroup. Whenever you restrict to elementary abelian subgroup, and if your module remains projective, when it is projective over G. Yeah. And now let us go to superalgebras and supergroups. So the first thing which we can do, and this is very natural, we can define splitting subalgebra, or in the same way we can define splitting subgroup. I will talk interchangeably between these two. If the restriction functor induces on the extension and embedding on all extension groups. And clearly, this is the same situation, works for them. We can detect projectivity by restriction for the splitting subgroups. One important lemma is that if K is a splitting subalgebra in G, and we look at this homological elements, G1 home, and we look at the orbits, but every orbit must intersect K non-trivially. So if you have this special element, which we call homological, when it orbit necessarily intersects a smaller one, and this is a necessary condition. We can also work with supergroups. It's a little bit more convenient. Why? Because it becomes clearer in a moment. The definition is verbatim the definition for finite groups, for the splitting subgroup. The only thing which we require that our subgroup inside the group must be also quasi-reductive. So we have one quasi-reductive group sitting inside another quasi-reductive. So this is one of the theorem, which, okay. So look what this theorem says. So if we have quasi-reductive subgroup K and G is splitting, if and only if the following condition holds. So if I induce from K, from the trivial module, what I get is a homogeneous space. I take a coordinate ring of this homogeneous space, and the constants should split as a direct summand over G. Okay, this is exactly the statement you have for finite groups. what is the main difference here? The main difference is that now when you induce, you get something very infinite dimensional. And what you actually have is an affine super variety. And then you are really in the situation of super geometry, which is nice, actually. It's just nice. What is this condition too? But basically, if I can define what is this volume, what volume counts? Volume counts you the number of elements, right? So what it says here, if I want to translate it back to finite groups, so it says that the index is relatively prime to P, okay? So now I should explain very little about it because about this super geometry. So first of all, you should think about something very simple, like unitary trick. So in the usual case, if you study reductive groups over C, you can go to compact form. You have hard measure. You can take the volume. So in supergeometry, you do not have top degree form. You do not have determinant on quantum, but you have Berezinian. So you have a volume form. And you have what is called Berezin integral. There is a way to integral functions on a super. And so Berezinian sheaf, you can think about this as a determinant sheaf. And then you can integrate it. And if this volume is just, if you integrate the identity, if it is not zero, then your group is splitting and vice versa. So there is a brief sketch of the situation. It's actually was.
Volume only depends upon the even part, or it does depend upon the.
It depends on the odd part. So what you do, you have the odd part, right?
Yes.
You have the top degree. You pick up the function there, and then you integrate it. Okay, so you have a coefficient of the top degree in odd variables, and you integrate it. And then, of course, this is an analytic thing. You have partition of unity, and you can do it over compact things. Okay, and the point is that if your group is splitting, you necessarily have invariant volume form. And when you can talk about the volume, although it requires, actually, it seems simple, but it took a lot to prove it because okay, so first of all, there is a duality in some way between structure sheaf and Berezinian sheaf. So, and Berezinian sheaf gives you the integral, but this is complex affine variety. So you have to take the cycle on the underlying variety. But for you, Sharon, it's clear you have compact form of G mod K, right? So you take compact groups. You have, and you take the integral. This integral is invariant. And physicists used it a lot. I actually found it without much justification written paper first. But anyway, what we did with Vaintrob, we justified and we used certain methods to compute these integrals. But then after that,
if one and two previously, are they equivalent?
Yes, they are all equivalent.
They both are.
They both are equivalent, and this is exactly mimics usual finite groups. Only you have to go to this integral and all this stuff. But in the end of the day, that gives you absolutely the same result. Okay, so basically this wild unitary trick after that. All right. So as soon as I have the integral, which is invariant, and I want that one is splitting, I need this, and this is unique. I need that this integral one is not zero, which is exactly what I'm saying when I say volume is not zero. Computing these volumes is an interesting story in itself. For example, you can compute volumes of super Grassmannians, and they are given by very nice analytic functions, G functions, some special series of special functions. This is a different story. I'm not talking about it today, but okay, let me continue. So of course, now we say, okay, the subalgebra, or if you want the subgroup, it's going to be the same in this case, is the Sylow subalgebra if it is minimal splitting in G, right? Exactly like in. So now we want to talk about this splitting subgroups, minimal splitting subgroups in particular. But you remember the minimal splitting subgroup is a P group. in the previous story, right? So what it is here, what we can say about the structure, are they all conjugate, and some other questions like this. Okay, and so now I'm going to introduce the new term, Ouroboros. Let's say quasi-reductive superalgebra or supergroup is Ouroboros if it is a Sylow subgroup in itself. Okay, so equivalently, it doesn't contain non-trivial splitting subalgebra. So an Ouroboros subalgebra should be thought as an analog of a P group. And it's more or less clear that from the previous definition, from the previous theorem, that a Sylow subalgebra, whenever it sits in any superalgebra, must be Ouroboros. Now you can ask me, what is this Ouroboros and why it is Ouroboros? So before we called it zero subalgebra. This is a very recent project. And when we got criticism from Julia, from Jordi Williamson, from other people, so we realized that we should come to something else, and this is just try. So this is Ouroboros, okay? So first of all, it reminds the sign of a dragon eating itself from the tail. It has several. So first of all, it looks like zero, right? And second, it's a some self-consistency, right? If you want the Sylow subgroup, it must be it the same. So at the moment we use this term, I don't know, maybe it doesn't survive, but we would like to try it on you. Okay. So now we come to elementary abelian groups. We say that the Lie superalgebra E is elementary quasi-toral if it's even part central in E, and it is given by the commutator of the odd part. So the following superalgebras are elementary quasi-toral. These are odd abelian Lie superalgebras, of course. These are these Q1 products of Q1. Okay, the product of two elementary quasi-toral is quasi-toral again. Or you can take SL11, and this is also quasi-toral, and we can take their products. So it's not very difficult to see that they are Ouroboros, and they should be viewed as the analogues of elementary abelian groups in our setting. So in particular, we expect that elementary quasi-toral subalgebras control much about our category.
Oh, sorry, actually, so these actually detect the homology.
No, yeah, they also detect homology, and I will talk about it. You're right. I will talk about connection, yes.
Homology.
But we have some Ouroboros, which are not elementary quasi-toral. For example, Q2. Or periplectic of order 2. So here is a more general example of Ouroboros subalgebra. It is related to loop in some strange way. Suppose I have a simple finite dimensional Lie algebra. And suppose I have a Grassmann algebra in one variable. So psi is odd and psi squared is 0. And so I take all the loops. So what does it mean? That I have S plus psi S, and psi S is a joint representation of S. And then I add a derivation, T d psi, which is an odd derivation. So that gives me the new superalgebra. We call Takiv superalgebra. I don't know why it's called Takiv actually, but it has interesting representation theory actually. Quite non-trivial. There is a paper of Cheng and Colombier on the representation of this. And it is also Ouroboros. It's very easy to check, but this is Ouroboros. And I think Q2 portion by the center is an example of such when S equals SL2. Okay, it's subalgebra. If I drop derivations, it's not Ouroboros. So what I can do, I can now take the products and I can take certain subalgebras inside them. And we can build basically, these такие algebras and elementary abelian are building blocks of all these parabola superalgebras. So here are several examples. Method. This is actually parabola takif. So you take direct sum of these loops, and you take subalgebra derivations, satisfying this condition that commutator with the odd part gives me the whole even part. And this is typical parabola takif. So here is other characterization of this. We got a little bit obsessed about these superalgebras, and we will see in the end why. So all these properties are hold. I'm not going to talk more about it because it may be a little bit technical here. But I would like to say that we have a different characterization of it. And here I would like to a little bit switch to the different important cones inside odd cone, inside odd part of the superalgebra. So you see, we actually study geometry of G0 action on G1 in order to describe the support variety. And so we can have this self-commuting cone I was talking about. We can talk about nilpotent cone in the sense of in the sense of representation theory. Is it better with light or no light?
It's fine. Yes.
Whatever. Should I continue or not? Okay, so wait. Yeah. There is there is a work on Nakano, and also then Nakano also work on Nakano with his students. And then there is this, my work of Ina and Eisenblatt, which Jacobson-Morozov is not true for all elements, which can consider only odd elements, which can be embedded into OSP1, 2, which is an analog of SL2. So there is this element which we call need. They are very important for representation theory. And when we have characterization, Ouroboros is equivalent, but it has no simple ideals. But its nilpotent cone is a self-commuting cone, and it doesn't have neat elements. And the last is more down to earth. You take odd abelian, and you take Ouroboros takif, and you can take their product, and you allowed even central extension, and you're still in this class of Ouroboros. So so any oddly generated subalgebra, Ouroboros, superalgebra is again Ouroboros. When it's not very difficult to check that the Sylow subalgebra is a splitting Ouroboros subalgebra. But there are differences, and one of the differences is that maximal P subgroup is always splitting. Maximal Ouroboros subgroup might be not splitting. We can classify maximal Ouroboros subalgebras probably. It's probably not difficult. We don't know, however, their representation theoretical meaning. But for Sylow, we have Sylow theorem, and I'm going to talk about it. Okay, so this is a picture. What is the difference? The reason is we have more Ouroboros subalgebras, which are big. The size here means we can have big Ouroboros subalgebras. So you see, this is 0 superalgebras. 0 is not changed to Ouroboros. It's from the previous talk by collaborator. But anyway, so here is the list for all classical superalgebras, which I gave you the list in the beginning of this talk. So we have this basic classical, exactly Sylow Futorny was talking about. Those have a nice notion of defect, and the Sylows are just the products of SL1, 1D. So in this case, my Sylow subalgebra is elementary total. It's an analog of elementary ability. In other situations, these strange situations of periplectic, of isometric, we have really Ouroboros, the products of Ouroboros. But they're all coming with an SL2 inside them. And so if you look at the detecting superalgebra of Kujawa and Nakano, they're exactly Sylow subalgebras. I'm not sure they did it for P. And what is important when we are talking about this stack, we can take a homological element of this Sylow subalgebra, we take the normalizer of it, the quotient bijection of normalizer, and then the stack is equivalent to this. So it's homeomorphic to the corresponding stack in this big superalgebra.
Sorry. So the detecting super algebra agree with the Sylow only in like the first clause, but in the two and they don't.
I thought they do. This is not a, what I say, this thing detects projectivity for sure.
Yeah, ours don't.
Yours not, but maybe then okay, so those are quasi-total one. You take quasi-total, yeah. This is the whole point of the situation, but I think in one of your paper you encounter this, right?
Yeah.
No? Okay, so maybe I should tell you how we get this list. So this is work with Vaintrob and previous work with Alex Sherman. So you see, first of all, whether we consider the homogeneous space, remember this is some affine supervariety with the volume form. I have to compute the volume, and I have to check that the volume is not zero. It is very tricky to compute this volume, but fortunately, what you can do, so you know maybe there is Destermatt-Heckman formula when you reduce your integral to fixed points of the torus. So there is analogous formula in supercase, which is called Schwarz-Zaboronsky formula. Here you take odd vector field, exactly homological odd vector field. If you have isolated points, you can compute your integrals using this contribution. So it's pretty subtle work, but in the end we get that all these are exactly Sylow subalgebras in our situation. So then we prove, what is it? Existence, first Sylow theorem, it's trivial in our definition. The second, that they are all conjugate. We proved it, but we don't have such a nice conceptual proof as we have in for finite groups. So we really do it step by step, and we use my old result about describing in some way of quasi-reductive superalgebras.
So for the Sylow subalgebra, it depends upon the choice of the design.
Of course, what I'm with Sylow, I mean, I fix characteristic P, right? And then everything is there. In this case, it's characteristic zero. That's why we first call them zero subgroups. So our situation mimics positive characteristic. But it depends on P, okay? When I say Sylow, I mean fixed P. In our case, P zero, okay? Yeah, so they are all conjugate. And then it's actually a third Sylow theorem, but don't have time to talk about it, but you can ask me if you are interested. There is also third Sylow theorem somewhere, as we understand that. So now I'm going to this projectivity criterion. So this is our recent work with Alex Sherman and Julia, and it just finished because one little step was done pretty recently. Suppose G quasi-reductive, and I have any representation in my category. And then minus projective isn't only, it's restriction to every elementary quasi-total subalgebra is projective. So it's exactly analog of Charnock theorem, okay? So you take on any elementary quasi-total subalgebra and it is projective. So here I give you this proof sketch. So first really strict to a Sylow subalgebra. And it's enough to prove it for Sylow subalgebra by the obvious reason. And we and therefore we reduce our statement to these Ouroboros subalgebras or subgroups which I discussed before to such a length. When we look at the structure of this oromorphism, and it has order billion part, which is trivial in this situation. And we have this takif. And this takif is pretty technical thing. So we have these slight extensions of, like, we want to take several Q2, product of Q2, and we want to prove this theorem in this situation. So we manage it, but it's rather technical because if I just take one takif, it has two elementary quasi-abelian subgroups, and these two quasi, you should glue it together. So that was holding this result for some time, but now we finally proved it. So now I go to this is the support variety projectivity detection. So if M is projective, and only if for any homological element, maybe after extension of scalars, this functor is 0. So basically we have the trivial support after extension of scalars. This extension of scalars actually comes from the old result on Grassmann algebra, right? Because we somehow already reduced it to quasi-abelian. We take quotient by center without any damage. And when we in a situation of Grassmann algebra, and here we use the old result, I think it is due to Luchazarov-Ramov, if I'm not mistaken, that it detects projectivity for, but it also probably follows from PGG correspondence. So
this position L, absolute value, is it the transcendence degree?
Yeah, you need transcendental extension, yes. Cardinality of transcendental degree.
The transcendence degree, what is L?
L is a field extension, transcendental extension.
Right. So, but the absolute value of L means the transcendence.
I mean, it's cardinality of L itself, but it is related probably with transcendence degree.
What's that saying?
It is related to transcendence degree, of course. It's the cardinality of, dimension of L. It's cardinality of dimension of L. So you see, that's the problem. And I have what I need, basically, what I have, and linear operator, and I want it to be at some point in the spectrum of it. That's why I need to take transcendental extension. When you prove it, for example, for Grassmann algebra in two variables, you already encounter this problem. But at some moment, you have to check that there is a linear operator, and it must have eigenvalue, more or less. Maybe we discuss details later, if because I think I should stop. Okay, so there are some corollaries. So if M is countable dimension and we work over C, there is no problem. We don't need to extend scalars. If M is finite dimensional, well, we can, for detect projectivity, we can use homological support separately and associated variety. And in some cases, we even don't need homological support. We need just associated variety. For all classical super groups, for example, this old variety of Le flow is enough to detect projectivity. Okay, but I'm close to the end. I would like to talk about further results and questions. So first of all, we have nice theory. We try to build a theory of green correspondences with vertices and how it's called, you know, green correspondence. We have one nice result in this direction, namely, if we consider in the composable representation of non-zero superdimension, we can relate them to normalizers of the Sylow subgroups. We have theory of defect groups and blocks. And we have a nice result, which we didn't write up yet, that in the case when your defect group is, a defect is one, we have equivalence of stable categories. Like in the there is a classical result for finite groups in this way. We're still struggling with this reusability, which we need to prove the conjecture. So we want to say that every closed conical support subset here is support of some finite dimensional module. And this is the last thing I would like to talk about, but probably shouldn't, that what I really believe is true, that you can extend this functor ds for all odd elements in a way and take simplification. And so you have some sort of the functors from a stable category to derived category of coherent, quasi-coherent shapes on G1, which are G0 equivalent with good properties. And that, if we can do that, we can cover our conjecture pretty straightforward. And now this final slide, I have some literature here because I believe it might be on some website. And I would like to wish them happy birthday and thank him for his work, which inspired me and my collaborator. And thank you very much for your attention.
Time for maybe one or two quick questions or comments.
So recently, we actually, my student and I looked at the homological spectrum that Paul Balmer defined. And it turns out that your splitting subgroups are very important to actually complete those stuff. It's essential to actually make the computation.
Yeah, this is yeah, I think I will, yeah, okay,
So
yeah.
I think it's a great tool.
Yeah, thank you.
You use a lot of geometric techniques. I think the answer is maybe no, but is there any hope in positive characteristics?
Oh, this is very good question. I think I will look at it as soon as I finish of some part of this story. I don't know. Periodic integral exists in principle. You can think about it, but you can combine. You should combine characteristic. So all is a zero characteristic, but it catches the important part. That's my belief.
All right, we're on a tight schedule this morning, so let's thank Vera again. And the next talk will be in 3 minutes.
Oh my.